Today we will be discussing the theories and experiments explored by our group dealing with software-defined radio technology. Our group includes Mr. Andrew Chiles, Ms. Shaughnessy Scott, and myself, Ben Rankin. We hope you enjoy learning a little bit about some of the interesting applications of software-defined radio, or SDR. To provide a brief outline of how this talk is organized, first we will give an introduction to what SDR technology is and a brief history of how it came to be. We will then discuss the central hardware and software components of SDR. After covering the foundational topics, we will then proceed to discuss our various experiments and applications done with SDR and conclude with some final thoughts. RF technology has played a pivotal role in many areas of our global society since the turn of the 20th century, including scientific, commercial, and military domains. RF transmitters and receivers are made up of many hardware components and circuit paths that traditionally have defined what types of signals that radio can send and receive. Think of traditional radios as hardware-defined radios. While this platform allowed many advances in the technology, it was still limited by the static hardware design of each given device. So what is software-defined radio? SDR, as its name implies, is defined by software rather than by hardware. A hardware-defined radio receiver for a set range of frequencies using a set modulation method could only ever receive those specific signals, whereas SDR has the capability to virtualize many of the hardware components and circuit paths that process the RF signals and can be changed or configured dynamically on the fly, such as changing modulation techniques, frequency ranges, filters, etc. Here we will provide an abbreviated history of software-defined radio. In 1985, the term software radio was introduced by E-Systems, the present-day Raytheon company, in an internal company publication and described the dynamic capabilities we've been discussing as a technology the company wanted to pursue and develop. In 1991, the U.S. Defense Advanced Research Projects Agency, or DARPA, initiated the Speakeasy project, developing a software radio that could use many different transmission protocols and send and receive on a wide range of frequencies. Fast forwarding to the early 2000s, the GNU Radio project was born from another project at the Massachusetts Institute of Technology, or MIT, which has become an open source platform for projects building custom SDR solutions. As we can see, SDR has grown very quickly and continues to be a vital part of many emerging technologies such as mobile devices and new versions of older devices. Next, we will take a look under the hood and discuss some of the specific hardware and software components of SDR. At this point, I'll turn the presentation over to Shaughnessy.
Next, we'll talk about the hardware and the software that we use for our project. The core hardware is the RTL SDR, the Realtek software-defined radio. It's a digital video broadcasting USB dongle that allows you normally to watch HGTV. That's HD as in Delta on your computer. The prices for these dongles ranges from $20 to $100 depending on the chipset used. It's the most important aspect of using these devices is that you need to get the right libraries. The libraries are going to allow your user-level applications to interact with your chip in conjunction with another library like libUSB. The range for these devices is somewhere between 24 megahertz and 1250 or 1776 megahertz, as you'll see on the next slide. Other than the extremely low cost, a great advantage is the sheer number of open source projects available. The downside is that they don't have any transmit hardware, they can be very noisy, and they operate on a lower range of frequencies and more expensive models. So you can do a lot with it, but maybe not everything that you want. The next model up is the Hack RF Jawbreaker. The Jawbreaker is capable of half duplex reception and transmission. This will run you about $300, and the performance of this varies a little bit based on the operating frequency. There's more on that in the paper, but this is a very exciting project with a lot of possibilities, and there's even a Kickstarter funding available for the next version that's going to come out and do even more than the current one does. The third option we have is the Edis Research USRP, made by Matt Edis. It's a low-cost, high-bandwidth software-defined radio. It was originally kind of trying to bring HD TV to the people, but the USRP has so many applications, there's so many models. This will run you from about $675 up until, I guess it depends on how much you want to spend. I think $1,100 is the max. The USRP was actually designed to be modular, so in addition to the board by itself, you can get a number of daughter boards to modulate the frequency to where you need it. Next slide gives an example of the comparisons. The USB dongles, as I mentioned, go from about 20 megahertz up to 2.2 gigahertz. The USRPs have an even wider range, but if you look, maybe not by so much. The USRPs have the most bandwidth, they're full duplex, high sample rates, very, very fast interface, and, well, you get what you pay for. But, as you'll see with some of our experiments, not necessarily with the R820 dongles. They're actually very, very, very versatile. The SDR software we used, of course, the drivers because we wanted not to watch TV but to do a couple of experiments. We also used SDR Sharp, which is made in C#, as you would guess. It's Windows-based and it has a number of plugins to support basically any application you can think of, including decoding iCars data, GSM, ADS-B, broadcasting over TCP/IP, just whatever you can think of, and also the new radio companion. New is a little bit more robust. It's Linux-based, and using kind of a modular approach, you can build any kind of system that you would in physical hardware in software using their software modules. And Baudline, of course, is a visual way that you can see the signals and analyze them for visualization.
Thanks, Shaughnessy. Now that we have covered the background and the basics of SDR technology, we will move on to some practical applications with several experiments with SDR and share our procedures and results. FM radio is one of the most common and well-known public uses of RF transmissions. This section will briefly address this type of signal and demonstrate the ease of receiving FM radio transmissions with a software-defined radio. FM, or frequency modulation, is actually a signal modulation technique used for more efficient use of the spectrum by varying the frequency of an analog carrier signal or wave. This has many applications in the realm of RF beyond just delivering your favorite songs or news programs to your car's radio receiver. However, FM radio, as it's come to be known by most, refers to a specific portion of the RF spectrum from 88 MHz to 108 MHz, with 200 kHz channels for separation. This is used for broadcasting audio signals primarily, however it can also carry data as well, as shown in the following experiment. With a typical antenna, the software-defined radio can be adjusted to the per modulation technique, in this case wideband frequency modulation, and frequency range, and it can be configured to leverage the standard computer hardware to receive these signals. While this is a very basic application, it demonstrates the concept of the software-defined radio's dynamic capability. On this slide, we see the results of the experiment configuring the software-defined radio, SDR Sharp, to use the wideband frequency modulation, or WFM, using the Blackman-Harris 4 filter and tuned to the 86.600 MHz frequency using a 50 kHz step size. We can also see the data transmitted with the audio signal displaying the name and website of the radio station that is broadcasting, mystar99.com. The signal carrying the audio and the data can be seen visually on the waterfall graph in the screenshot. Now that we have established the concept of software-defined radio being able to turn standard computer hardware into a virtual radio capable of receiving a certain type of RF signal, next we will move to more advanced experiments using software-defined radio. One less commonly considered source of radio signals is from orbiting satellites. These types of signals are only available to a given point on Earth at limited times and require specially designed antennas to capture, but they are all around us every day. One of the more interesting types of satellites are weather satellites, such as those owned by the U.S. National Oceanic and Atmospheric Administration, or NOAA. Our goal in this experiment is to demonstrate that the reception of these signals that has historically required a specialized receiver can be done with a specialized antenna, software-defined radio, and standard computer equipment to showcase the versatility of software-defined radio. This will also demonstrate the relative ease of capturing satellite RF signals for analysis if some information about them is known, like the frequency. NOAA has 3 active weather satellites currently in orbit in complementary orbital paths around the Earth: Satellite 15, Satellite 18, and Satellite 19, which broadcast RF signals down to the Earth on 137.62, 137.9125, and 137.1 MHz respectively, using right-hand circular polarization due to their orbit. These satellites take measurements and photographs of the atmospheric conditions below. These photographs are broadcast down using an automatic picture transmission, or APT, audio signal. In our experiments, we attempt to capture and decode these signals and receive the satellite weather images using everyday equipment and components. The first step in our experiments is calculating the wavelength and the quarter wavelength for the frequency that we want to receive, which is the 137 MHz band. Using the standard formula as shown on the slide, our calculations have us arrive at a wavelength of 2.189 meters, which will be very important in our calculations during our antenna design phase. The next step is our antenna design. We have to select an antenna type that is capable of receiving right-hand circular polarized signals. For this we have chosen the quadrifilar helical antenna. The antenna elements will be made from 3/8 inch copper tubing connected to an RG6 coaxial cable mounted on a PVC pipe mast. All of these items are available for purchase at a local hardware store. The antenna, as shown on the following slide, consists of 2 helical looping elements, one loop being shorter than the other, that are connected at their ends to form one large element. The antenna design can be seen here, as well as a view from the top depicting the connecting segments of the elements before the RG6 coax cable is attached. This design is beneficial for receiving signals from orbiting satellites due to its ability to receive omnidirectional or complete hemispheric signals. This is due to the fact that the source is constantly moving across an arc above the surface of the Earth from a constantly changing angle. Other antenna types can be used for this if they are mounted on a calibrated rotor that is in sync with the satellite's path and rotates the antenna during the satellite's pass. However, this approach is much more efficient for the purposes of our experiment. We will now briefly discuss the software packages used for this experiment. SDR Sharp is our software-defined radio solution, which is described at length in another section of this presentation, so it will not be discussed in depth here. Orbitron is a program that takes updated satellite path data from the Internet and tracks orbiting objects like the International Space Station, or conveniently, NOAA weather satellites. This program can also adjust the frequencies for Doppler shift, which is important for satellite transmissions. WX2IMG, or Weather to Image as it will be called, is a key piece of free software that decodes the APT signals into images. VB Cable is a virtual audio device that can be used to pipe analog audio signals from one program to another. We will now discuss the general steps for our experiment. The first steps were to place the assembled antenna outside with a clear view of the sky and to update the software that needs satellite tracking information from the Internet. Next, we used SDR Sharp and Orbitron to tune to the correct frequency to receive signals from the approaching satellite, NOAA Satellite 18. And to ensure that the audio output from SDR Sharp was being fed out and into the Weather to Image software for decoding. The next step was to wait for the next overhead pass of the NOAA Weather Satellite 18. Once this started, since the audio signal is being fed to the Weather to Image software, we had to visually monitor the waterfall graph to see the initial signals being received by SDR Sharp. Subsequently, the Weather to Image software was monitored to see if lines of the image were beginning to be decoded from the audio tones. Once the satellite pass was completed and the signal faded away over the horizon with the satellite, weather-to-image software was used to process and correct the image received. Here we can see a screen capture of the SDR Sharp software capturing satellite signals from the NOAA Satellite 18 on the 137.9125 MHz frequency. The following is an audio sample, taken when we were not decoding APT images, that carries the APT signal. Note that the actual analog audio tones and not digital data is what the software decodes the weather images from. Here we can see the Orbitron software tracking the 3 selected NOAA weather satellites and currently displaying information about the NOAASat 15. This software displays the future paths and past tracks of the satellites as well as their current location over the Earth. Here we can see the weather-to-image software decoding the uncorrected weather imagery while it's receiving audio signals from SDR Sharp. Note that there is a slant to the image that is later corrected by a processing feature in the software. Details of the audio signal and about the current satellite pass in which satellite is being received are displayed by the tool. Here we see a cross-section of the final product of the experiment, the current satellite weather imagery of the atmospheric conditions over the location of the ground station in Huntsville, Alabama. This image shows cloudy conditions over the southern Atlantic coast and clear skies over the state of Tennessee. Our objective in this experiment was to demonstrate that with some knowledge of the signal type, primarily the frequency, and knowing when the satellite will be passing overhead, a moderately sophisticated attacker could potentially monitor or intercept satellite signals not necessarily intended for them. While these signals for the NOAA satellites are obviously sent unencrypted and details of their transmissions made public, it is still a demonstration that an antenna can be built and signals received with a relatively low overhead cost. All the equipment used in this experiment was purchased for less than $100 and was found at a local hardware store. That concludes this segment of the presentation. I'll now hand the presentation over to Mr. Andrew Chiles to talk about his experiments.
Thanks, Ben. As Ben said, my name is Andrew Chiles. I'm going to discuss the next few experiments that we performed with the SDRs. I'll start with the Automatic Dependent Surveillance Broadcast, also known as ADSB. This is the next generation aircraft positioning broadcast system that essentially replaces lots of ground-based radar stations with onboard global positioning system or GPS devices on the airplanes that allow the airplanes themselves to track their location and then transmit that back to ground stations. By 2020, all commercial aircraft in the U.S. should have this technology, and most already do, but it's mandated by 2020. ADSB operates at 1090 megahertz, and it transmits basic information like altitude, heading, position, speed, and the aircraft's flight number. This is all unencrypted communications. It's a public standard, so you can go out and view that on the FAA website. And for this particular application, our goal was to correctly receive and then demodulate the signals in order to plot the GPS coordinates on a map. Fortunately, there are a lot of SDR software packages already developed and open source available for us. SDR Sharp we used again primarily just to view the spectrum and prove that we were actually receiving in the ADSB signals by tuning to 1090 megahertz, and it's essentially just making sure we were getting those bursts back. Dump 1090 was the primary application we used. It's a Linux-based C application. You can get it on GitHub at the link you see there. It's extremely easy. It's command line based, but it also has a graphical component in the form of a web browser. So if you, with the right switches, you can actually view a local Google Maps instance where it will plot the airplanes on the map for you as the frames are correctly received and decoded. For a Windows side, you have to use two different applications in combination. The first is ADSB Sharp, and that essentially decodes the signals and then opens a socket that will stream the raw bits back out. And Virtual Radar is another GUI type application that relies on Google Maps to take the data from ADSB Sharp and plot it on the map. A unique part of this experiment was the antenna we used to receive the ADSB signals. The signals are linearly polarized, so technically we could just use a wire antenna, just a little whip length of coax cable, but we wanted to optimize the range of the aircraft that we could receive. So there's a lot of publicly available plans on the internet for these type of antennas tuned to 1090 megahertz. We chose to use one from ARRL, the Amateur Radio League, and the link of the guide we actually use is at the bottom of this slide. But essentially, the type of antenna is a coaxial collinear, which is a collinear antenna made from just RJ6 coax cable. The calculations we used are you can see in the equation to the right, and we used 8 elements, and so are approximately a half wavelength, which is about 4.5 inches when you account for the velocity factor of RJ6. Basically, that's just accounting for reduction in the speed of light through the RJ6 cable. Here you can see our completed ADSB antenna. Each element are heated in the oven to make them pliable enough. Then they're joined together by pushing the coax between the outer sheathing and the wire mesh of the opposite element. We tested for shorts with a multimeter, and when we verified that there were no shorts, each section was wrapped with electrician's tape to give it more rigidity. One end was terminated with an F-type connector, typical coax connector, and then on top of that we connected a ENC adapter to connect to our RTL SDR device. These are basic procedures that we use to receive the ADSB signals using the Dump 1090 application. First, we made sure our listening station was outdoors, away from any kind of buildings, and get away from the shielding and EMI produced by being indoors. Second, we used a laptop running Ubuntu 13.10 and connected our RTL SDR device via USB. Third, we attached our collinear antenna to the RTL SDR with a BNC adapter, and additionally we used about a 5-foot length of coax cable to give us extra height when we mounted our antenna. Next, we used SDR Sharp and tuned it to 1090 megahertz just to confirm our signal reception and to see graphically that we're receiving those ADSB bursts. Lastly, we started the Dump 1090 console application in interactive mode with networking, and basically this lets us view interactively the frames coming in and the decoding in the console, and the network portion allows us to browse to a local port on our Linux machine and then view a Google Maps instance with those planes plotted on top of it. The maximum distance of any plane that we received was approximately 97 kilometers from our station in Huntsville. Since ADSB operates in line of sight, according to the FAA, the theoretical maximum is roughly 277 kilometers or 150 nautical miles. So we essentially got about a third of the theoretical maximum distance with our homemade antenna. We estimated that we could do better or get better reception than this if we placed our antenna on a higher mast. And the screenshot you see here is essentially the console output of Dump 1090, and behind that is the graphical output that you get when you browse to its virtual radar HTTP server running Google Maps in the background. To the right, you can see that we had 3 planes on screen: their altitude, their tail number, their speed, and their coordinates. In the center in the console, you can see a little bit more detailed information, such as their heading, the number of messages that were decoded, and the last time the plane was seen. For our conclusions, we wanted to note that the ADSB messages offer no authentication or encryption. This is what allowed us to easily receive and decode these 112-bit bursts from the aircraft passing overhead. It would not be difficult for us to construct an SDR-based transmission station designed to spoof legitimate aircraft or inject false information into the whole tracking system. You could also simply jam an ADSB ground station and blind them. Researchers at Black Hat 2012 in Las Vegas, Nevada actually demonstrated some of these weaknesses in their talk called Ghosts in the Air. And as you'll see with our additional experiments, the prevalence of SDR technology and the increasing number of open source applications designed to automatically decode them will definitely increase the chance of attack on systems like ADSB. Our next experiments focused on keyless entry systems. These are key fobs or keychain devices that you use to control vehicle doors, garage doors, home security systems, open windows, turn things on, turn things off, that sort of thing. They're typically very low power, and they operate on 315 or 433 megahertz for the most part in the United States. And they use simple amplitude shift keying or frequency shift keying modulation schemes. Our goal was to observe the keyless entry signals and attempt to replay a captured signal to open the corresponding door. Keyless entry system security is hit or miss. Modern implementations use rolling codes, but previous generations used often static codes or relied on dip switches that gave a static set of maybe 256 or 4096 codes you could choose from, just to prevent interference, not necessarily provide additional security. Today's rolling code implementations use a pseudo-random number generator both in the transmitting and receiving devices, and those are coded with a seed value. And then when the transmitter wishes to transmit a code, open a door, close a door, turn on a security sensor, turn off a security sensor, it computes the next code in the sequence based on that pseudo-random number generator and then transmits that. The receiver compares this received code to what it calculates the next code should be. And to prevent any desynchronization, say if you pressed your key fob for your car in your pocket while you're fiddling with your keys, but you weren't in range of your car, the receiving device in the car will have a buffer of, say, 256 codes that it'll compare against, just to prevent the desyncing. If the receiver determines that the correct code has been transmitted and received, it will trigger the corresponding action that was transmitted with that code. These are the primary software packages we use to receive and transmit keyless entry system signals. Again, SDR Sharp was used. Audacity is a new one. It's primarily an audio editing application, but we used it to view the amplitude shifts for the keyless entry systems since they were extremely simple signals. GNU Radio Companion was used this time. We used several flow graphs to import the IQ data that was generated by the HackRF transfer program. Baudline is another graphical viewer into the spectrum that we imported the IQ data from HackRF. And finally, HackRF transfer was a C-based utility provided with the HackRF libraries for the HackRF Jawbreaker device that we used to actually transmit our captured signals. The first keyless entry systems we focused on were vehicle-based. In particular, we targeted a 2002 GMC Envoy SLT remote. We began by looking up the FCC ID on the FCC website for the operating frequency of this remote and found that it was at 315 megahertz. Next, we used an RTL SDR and SDR Sharp with a simple wire antenna tuned to 315 megahertz and captured that signal. This was demodulated in SDR Sharp as an amplitude modulated signal and then exported as a simple wave audio file. This resulting wave file was opened in the Audacity audio program, and then there we could examine signal amplitude shifts using its zooming features. Here we can see a view of the GMC Envoy's key fob signal when the unlock button is pressed. This burst is actually transmitted twice on every key press. In the first screenshot expert, you can see a single burst. And it's interesting that there is a preamble at the beginning of the signal, and then it kind of trails off, and then the actual data starts. And this is repeated twice for every time that you press any operation button on the remote. On the second screenshot excerpt, you can see a zoomed view of the data of the signal. And here you can see essentially the pulses, the ones and zeros of the signal. And it looks like a fairly large code is being transmitted, which is to be expected with modern rolling code systems on vehicles today. We also assume that Manchester or some form of encoding was used so that the actual codes transmitted are actually probably a lot smaller than what you see here. And we have an excerpt that we can play for you. And that was 4 presses, 1 unlock, 1 lock, unlock, lock. At this point, we didn't go any farther with the vehicle systems, and we started shifting our focus towards garage door systems, which are a little bit simpler and have smaller codes to deal with, and you're less likely to mess up the receiving system in your car and desync your key fobs. Garage door openers are extremely common in today's households, and they essentially just allow remote automatic opening of a garage door. There's really only a few manufacturers, and the largest of these is Chamberlain, and they have a lot of different generations of security features, as I mentioned earlier. The initial openers had no replay protections whatsoever. It was just a factory hard-coded code. So if you and your neighbor had the same version from the factory, you would open each other's garage doors. The next generations relied on dip switches, which didn't really provide security. They just prevented interference from your neighbors to keep them from opening your own door accidentally. So these would typically be 8 to 12 dip switch systems, which equates to 256 or 4,000 codes. However, current generations use rolling code technology of 32 bits or greater, which are into the billions of codes. You can see in this excerpt from Wikipedia below that we're currently using Security Plus and Security Plus 2.0 rolling code systems on early 2000s and later garage door openers. The one we focused on for our experiments is actually a Security Plus, a 1.0. Here you can see the Chamberlain LiftMaster series garage door opener and remote that we targeted for this experiment. Our research found that the device uses a form of amplitude shift keying called on-off keying, which is just like Morse code. A signal being transmitted equals a 1, a lack of signal equals a 0. This is great for a device such as these because they're really low power and low cost, but they have limited range, which is okay because you're usually pretty close to your garage door when you want it opened, and they're very susceptible to noise, and we'll see compensation for that in the received signal later. Just like the key fobs, this also operates on 315 MHz. So to capture a garage door opener signal, as I stated, we looked up the FCC ID on the FCC website for its operating frequency. We were also able to obtain various engineering specifications, circuit layouts, and user guides on the FCC website. For this experiment, we actually used our HackRF jawbreaker device and a log periodic antenna connected to a laptop with Ubuntu 13.10. And for this experiment, we chose to use the HackRF because of its transmit capabilities. Next, we recorded the signal with the HackRF transfer utility and GNU radio as raw IQ data, and you can see the command that was run there. Essentially, we captured at 315 megahertz using a sample rate of 8 megasamples per second, and the rest of the settings are gain. Next, to view our captured IQ data, we loaded them into GNU radio and viewed it in the scope plot, and also into Baudline and Audacity, just to get different views of the same signal. We found that each press of the remote results in 8 bursts of 21 pulses apiece. Each of these pulses is approximately 41 milliseconds in duration, with a 60 millisecond gap between the bursts. The first 2 bursts are repeated 3 times. So essentially it's 2 bursts, 2 bursts, 2 bursts, 2 bursts. And we assume this is because of the potential RF interference in the 315 megahertz band and the fact that the on-off keying is very sensitive to noise. Here you can see one of the GNU radio companion flow graphs we used to import the HackRF IQ data. The HackRF transfer utility actually stores IQ data in a more complex format than GNU radio is expecting. So we had to define and tweak a flow graph to convert this IQ data into a form that GNU radio could handle. And this was the result. Here you can see our garage door opener captured signal in Baudline. The first screenshot is the full 8 burst sequence, which is actually 2 bursts repeating 4 times. Again, this is probably due to prevent interference or deal with interference and prevent a user from having to repeatedly click their garage door opener. And then you can see the zoomed view of the first and second burst. The lines on either side of the bright green we assume are harmonics or distortions produced by holding and overloading the receiving antenna by having the transmitting garage door opener so close to our HackRF. You can see that this is a much simpler signal than the one transmitted by the key fob for the vehicle. Note that there's no continuous carrier transmitted this time. It is essentially on and off. And there seems to be a fixed width between each burst, and the bursts appear to have approximately 3 different links, and we can only assume that these correspond to bit values. This is another view in Audacity, which just again shows you without the extra distortions how simple the signal is and how short it really is. There's not a lot of information being transmitted here. So once we had received the signal, we decided to try to replay it. We knew that traditional replay protections would prevent us from replaying and successfully opening a door and as it was typically operating. So what we had to do was capture the remote signal out of the range of the garage door. This way it would be a valid signal that the garage door opener hasn't received yet and would accept when it was presented with it. Next, we use our highly directional log periodic antenna with the HackRF, and this was used to direct our low power transmissions of the HackRF towards the garage door receiver. Then we used the HackRF transfer program again to utilize the Jawbreaker's transmission capabilities to relay the previously captured signal. Now, essentially, this is the same command as we used to capture, except we used a T switch to transmit, and then we altered the gain to raise it. Using this technique, we were able to successfully open a garage door with a captured signal. However, this only works once, as the code is invalidated after one use, which is essentially the replay protections in action. Here you can see a video of our replay. This is our simple setup with the log periodic antenna attached with the SMA connector to the HackRF board. And you can't see that here, but I'm trying to show you the HackRF command line that I ran. Simple press the enter key or once to open up the garage. In conclusion, the security in current keyless entry systems prevents typical replay attacks in most scenarios. Again, we are only able to replay a capture signal when the signal was not received by the intended receiver during the original transmission. Now, legacy systems that use fixed codes or dip switches are very easily brute forced using these types of SDRs and open source software. You can do simple Google searches and find several articles already online to open these door openers in a matter of minutes. These same techniques can be used to receive and transmit signals for home automation systems, weather stations, and even RC toys. There's several interesting projects online where engineers have reversed the on-off keying protocols and codes for RC cars and child's toys and are able to control them with their SDRs. And now I will hand the floor over to Shaughnessy Scott, who will discuss our next experiments and conclude our presentation.
Next, I'd like to talk about my experiment doing a trunked signal decode using the SDR Sharp software and the SDR USB. Trunked signals basically allow multiple users to share a single frequency band. Most commonly, emergency responders use the 800 to 900 megahertz band. A lot of different traffic in one area, and not all of it's used at the same time. So trunking allows multiple groups to determine what frequency they're going to use for what period of time, and then move between channels that are available. Trunking traffic has two signals, control and voice, and examples of trunked radio systems include Project 25, Motorola Type 1 and 2, Logic trunked radio, and the EDAX system. Most people probably aren't interested, but there are people who kind of, in the interest of neighborhood watch, want to listen to police scanners. Your husband might be a policeman, you might be a ham radio enthusiast, or you might be a person who's curious about learning more about RF, and that's what this is focused on. Next, I will tell you the options that you have available if you choose to do such a thing. You can buy a trunk scanner at a cost of $200 to $450, and that's on the low end. You can spend as much as you want. Of course, you can go online and listen to trunked broadcasts through a service called Broadcastify. It's a little bit like listening to any kind of online radio service. However, you may only have 1 or 2 streams from your area. There is actually an app you can get on your phone, and you can listen to trunked radio signals. But again, if you're interested in analyzing the signal itself, or if you're a person with other motivations, maybe you don't want them to know that you downloaded the police scanner app and them have access to your phone that way, or you have no idea really what kind of extra features may be in that freeware that's downloaded and what it's sending or receiving from your phone. So we chose to use the SDR and USB dongle, $20. So I mean, the $19 police scanner is kind of a convenient catchphrase. It's actually more like $40 if you set it up according to the directions I used, which have one dongle and the control channel, which chooses which frequencies to hop to, and another dongle as more of the voice decoder, where you can actually hear what's being said on the channels. To start off, you can go to a site called radioreference.com, and it's going to allow you to look up the trunk signals as well as all the other frequencies that the emergency fire response and local agencies or businesses are using in your area. It's completely free and accessible to anyone. For an additional fee, of course, you can get more information. And just below is a table that describes the common protocols that are used. In my particular county, they're using P25 phase 2 only. Some counties may be encrypted, but we'll talk a little bit more about that later. On the next slide, we'll talk about the software packages that are used. Again, every experiment so far has talked about a little bit about the software setup, so I'm sure you're familiar with SDR Sharp. Unitrunker is a new piece of software that has been used in the previous experiments, but this is used to decode the trunking signals. It's going to look at the control channels and allow SDR Sharp to follow the conversation across the available frequencies. And the other new piece of software is the digital speech decoder. This is going to allow the output of Unitrunker, once you get your control channel and your voice channel set up, to be demodulated or translated into something that we can understand and piped out through your speakers. And of course, we can't do this without the virtual audio cable. Everything's in software, so no hardware was purchased in addition to the USB dongles. On the next slide, we kind of go through the steps. Now, this is the 50,000 foot view. There are a lot of detailed steps in the middle, but this is basically the process. The first thing you do is you have to find a trunk signal in SDR Sharp. Trunk signals look kind of like what you see on the screen. There's even places you can go online and they'll show you what they're supposed to sound like. Not very pleasant to the human ear, but at least you know they're fairly distinctive, and you can kind of watch the signal hop across different frequencies. But once you find one that you like, one that's pretty constant and is not going to frustrate you while you set up the rest of your experiment, you can set up separate SDR Sharp instances for the control channel and the voice channel, so you'll be ready whenever you get your decode set up. You're going to pipe the output of SDR Sharp, that trunked signal, into Unitrunker so it can figure out the control signal and actually control SDR Sharp on the voice side to hop around from frequency to frequency. And the next step, of course, is to set up the input channels for control and voice in Unitrunker. So you get all your pipes ready before you hit play on that signal, and it's going to go straight through, as you see in step 5, and just pick it up and start decoding. You can't see the resolution on the slide, but and you don't of course have all of the details from radio reference, but the control signals that were given on radio reference match exactly what control signals Unitrunker picked up, and they're identified in different colors and various screens in the call history and the channels. Unitrunker even keeps a log that you can go back and look and see, hey, this is what I got on this date at this time in this frequency range. Step 6 is where the audio output from the Unitrunker was to be piped to the digital speech decoder, which would in turn decode the P25 voice signals into data that we can hear and understand, and pipe that through the speakers. If you look at this diagram on the left of the slide, you'll see kind of a illustration of how it's supposed to work. The two SDR dongles, one piped into Unitrunker, which is going to track the control channels and allow us to hop along to the available frequencies along with the police scanners. And the second dongle tuned into the voice or traffic channel and piped into DSD, which is going to decode the digital voice. Ultimately, it didn't work for me as our county uses Project 25 Phase 2, and that's not currently supported by any of the software that I'm aware of. But if you look at the screen in the middle, you'll see the attempted decode by the DSD software, and if you look very closely, you'll see it's saying, hey, this is P25 Phase 1, and trying to figure out what kind of signals. DSD will create a wave file, or will kind of record the signal as well as play it out to audio. But all's not lost. There are plenty of police scanners and police signals that are broadcast over regular FM, because they don't consider their communications to be particularly sensitive. Some counties encrypt or scramble the signal, and some just have it out there in the open. So I tuned to one of the local stations as prescribed in radioreference.com, and I was able to play a non-trunked signal. And I'm going to go to the next slide, and hopefully you'll be able to hear it.
85 Tango 6, still traveling south on 231.
Next, as a conclusion, decoding trunk protocols is another great application for software-defined radios. I wish I had the opportunity to go a little bit more into it, analyze the signal itself for P25 Phase 2 versus Phase 1. But, you know, we have a limited amount of time and resources. Also, you should be aware that listening to police scanners is great, but there are some caveats. It's illegal to listen to encrypted channels, and as we know, things being illegal usually stops people from doing that, or at least on the surface, right? It's illegal to listen to cell phone signals, and I think they're doing something called rebanding, and they're reallocating the spectrum, so not everyone is on the same spectrum they were on before. They're moving the emergency and fire users to a different end of the spectrum, so we're not interfering with one another. And it's also illegal to use any of the information that you get for personal gain. And I'm told that if you're found with a police scanner on you while committing a crime, then there's an addition to your sentence. So this is just the standard caveat you use when you're talking about something that is possible, but you want people to do so responsibly. Last but not least, encrypted transmissions as well as Phase 2 can't be decoded by DSD, and any known open source software that I'm aware of, you guys may find out differently. But this system may allow interested parties, we're not saying who might be interested in doing so, to passively analyze and study samples for patterns and potential weaknesses. So if you get enough samples and you get the open community cracking on it, or as with the HackRF Jawbreaker, if you get enough of a Kickstarter funding, and a lot of these programs started open source or research grant founded, then you can solve pretty much any problem. So it could be just a matter of time if they're not already doing it.
Thanks, Shaughnessy. In conclusion, we have discussed how SDR leverages general computing hardware to emulate or virtualize hardware components to allow dynamically configurable software radios, and thus opening the door for new applications and research. SDR technology has many open-source platforms such as SDR Sharp and GNU Radio that enable many new researchers and organizations to make advances in RF technology. As shown in our experiments, there is a wide variety of practical applications for this technology, most with relatively nominal costs. As with the introduction of any new technology, there comes the inherent risk of those who would misuse it for malicious purposes or for personal gain at the expense of other users. Intercepting communications, unauthorized cryptanalysis, surreptitious entry of facilities with keyless entry systems, and a host of other potential vulnerabilities exist. However, the new access for a greater number of researchers and scientists will create new advances and new mitigations that will typically outweigh any potential negative impacts. As more new vulnerabilities are uncovered or created by the attackers, new mitigations and countermeasures will be developed to combat them, much like how software vulnerabilities are managed currently. Software-defined radio is becoming a central part of many of our devices that rely on RF signals, and will continue to grow in popularity. The security community must remain vigilant to keep up with potential attackers and to maintain the security posture of wireless systems. This concludes our presentation, and we thank you for watching, and hope you've enjoyed learning a little bit about software-defined radio and the potential security impacts of its applications. Thank you.